we try to fix this one. Let's suppose we try to fix this one. Okay, we're going to put 1, do a different color. Let's fix it to see if we can do it this way correctly. So 1. Okay, with a little F for fix. So I think we're in agreement with 2. Because you could flip heads and heads, yes? You can flip heads and heads. Okay, totally fine. 2, tails and tails. I don't think anybody's going to argue that point. I also don't think anybody's going to argue that you could be heads, tails, tails. You could flip heads, tails, heads. But what else could you flip?
Tails, heads, heads.
And?
Tails, heads.
So technically speaking, what do we have to divide by now? Well, it looks like there's 6 things now, right? Go ahead and crunch that out for me. Go ahead and crunch that out for me.
Okay.
3 and some change?
2.666.
Oh, 2.6, I went too high.
Yeah.
2 point, not 2.7. Which is now a couple above the 2.5. Now, some people will say, wait a minute, that doesn't seem like it's that high. It's not that it's that high, it's that we do have a problem. We do have a problem. There is absolutely zero problem with this average right here. The true average, FYI, the true average is exactly 2.5. That should be the true average. If I let this experiment go infinitely, forever and ever and ever and ever and ever and ever, infinitely, the average is 2.5. Which means if I collected more data from you guys yesterday, notice how more of you took 2 than took 3, 100 to 81. That will even out over time. You'll have the exact same number taking 2 as taking 3. I want to come back to why that is momentarily. What happened here, though? Why is this going to 2.7? This actually, coincidentally, ends up being exactly the right number because there is an inadvertent weighting that happened up here. You guys didn't mean to do it, but you did it inadvertently. You weighted it properly. Putting 4 3s here and only 2 2s makes it look like what?
You'll have to roll, what, 3 times
More often. Doesn't it look like you'll have to roll 3 times more often? Twice more often. That's what this makes it look like. It makes it look like you have to flip 3 times, twice as much as you flip 2 times. Which is why the average is 2.7, not 2.5. But that's not true. That's not true. Think about why. Think about why. Flip the coin first. Flip the coin first, yes? What happens? Heads or tails, and it doesn't matter what you get at that point, does it? It doesn't matter what you get at that point. The next flip is kind of what matters. Now, so you got one coin. We'll do it. For those of you who haven't looked at your project yet, we'll do a little tree diagram here. We'll take a look at it. We'll take a little look at it. All right. First flip. Okay, start. Heads or tails. Now you flip a second time. Okay. What's going to happen? Regardless of what happened first, you're going to get heads or tails second. Heads or tails. Heads or tails. Now, if you flipped heads and heads, you're, that should be blue. Get out black. If you flip the heads and heads, you're done. You're done, correct? And if you flip tails and tails, you're done. You got your repeat, and you're done flipping. You don't flip anymore. What % of the time are you going to flip tails and then tails? 50% of this branch, but how about overall? 25% of the time. Each one of these branches is equally likely. That's what the project is trying to get at. That project for next week is getting at the idea that each branch is just as likely as any other branch. So each of these branches is 25%. 25% of the time, you're going to get tails, tails. 25% you're going to get tails, heads. 25% you're going to get heads, tails. And 25% you're going to get heads, heads. So 50% of the time, you're done after 2 flips. Does that make sense? Half the time, you're going to flip heads, heads, or tails, tails. Fair enough? Well, if that means that 50% of the time you're going to go heads, heads, or tails, tails, and you can't flip more than 3 times, doesn't that mean, by subtraction, that the other 50% of the time you're going to flip one of the 3 ways? Doesn't that make sense? Now, if it doesn't make sense, it's totally fine. Let's go to 3 flips. Let's go to 3 flips. Third flip. Now, I'm going to pretend to keep these branches going with dotted lines, even though they wouldn't technically keep going. We'd be done with this experiment. But technically speaking, this could go to heads and tails again. I'm going to use dotted lines because we wouldn't actually do that in the experiment. We'd be done after 2. But this one would need two lines, wouldn't it? Heads or tails? This one would need heads or tails? And this one, dotted lines, heads, dotted lines, tails. Believable? Even though you wouldn't actually do these 2 dotted line branches, they'd still be arguably part of this tree. Now, each of these is 50%. Each of these is 25%. What's each of these? Half of 25, 12.5%. These 2 technically don't exist because the 12.5 and 12.5 is wrapped up back in this 25. It's not gone. We just stopped back here. So there's 25%. Here's 25, there's 25 more. There's the other 50. And here's 25 more. So half the time we stop after 2, the other half the time we stop after 3. That's why the average is exactly 2.5. Amber, go.
Why would you even count those as percentage? Why wouldn't it just be another 20?
Oh, I'm just saying this tree can be used for any time you flip 3 coins. It's just that sometimes you don't want to count certain outcomes because you will be done before getting to them. In other words, if Apple was studying their iPod, oh, I got Dave Matthews twice. Stop counting. We don't have to go any further. We got too many. We have too many of a repeat. I'm not saying that you won't in general. It's specific. Right now, you don't want to count. Is that a fair answer? So, in other words, when you guys did the average wrong like this, you technically did the average right, even though you weren't accounting for all the outcomes. So it was just good luck in our case, I guess. Matter of fact, you could even keep it even simpler than that. You could have just done this. Because there's only 2 outcomes. And they're equally likely. You either flip twice, or you flip 3 times, and they both happen half the time, right? They both happen half the time. We'll study this at depth in 243 if you guys take 243. This is a huge chunk. We're in the middle of it right now. And it's going to take us like weeks to get through. It's the idea of the expectation of a random variable. But of course it is. Because the trick is you've weighted it properly. Now down here, the trick down here is we didn't weight the 2s and the 3s properly. We put 3 3s, somehow making it seem like those 3 3s were just as prevalent as these 2 2s. But they're not. They're half as prevalent as the 2 2s, aren't they? So technically speaking, what you'd have to do is multiply that by 1/2. Now this is where it gets annoying. I don't want to get into that kind of crap. You see, you don't want to have to go in there and start drawing trees, because sometimes if you're going to be flipping these things like 8, 9, 10, 13 times, you don't want tree diagrams going to 13 sets of branches. It gets pretty ridiculous if you've done the project after 4 or 5. It gets pretty ludicrous. After 5 and 6, you're like, time out, I'm done. Good for you, you should be done with that. But the idea is, that's where statistics comes in to rescue us. That's where statistics comes in. It lets us just run the experiment, collect the data, and do the weighted average from there. That's the power of statistics. It allows you to get the answer you need within a certain amount of error, but a much, much more efficient way. So Aaron, fantastic question yesterday, and well timed with where we were. Make sense? You guys buying this? Good. So on average, it takes 2.5 flips. Because half the time you get double heads, double tails, half the time you need one more flip. 2.5. Good enough? Good. Now, I'd like to look at another question related to your coins. Back to the Excel sheet, because I got the data here.